You've seen this image. Taken in 1995 by Hubble, the pillars of creation changed how we view the universe forever. Now imagine taking that exact same detail and zooming out 100 times. That's not science fiction. It's NASA's newest mega-eye in the sky. To put its massive power into perspective, a survey that would take Hubble an entire century to complete will take Roman just one single month. So Roman isn't just doing Hubble-era science a little faster. It's opening the door to completely new, wildly ambitious questions. In that first month alone, Roman can survey our entire Milky Way galaxy, mapping over 20 billion stars to create an astronomical catalog larger than anything humanity has ever built. And when it turns its sight towards the crowded center of our Milky Way, monitoring 200 million stars every 12 minutes, it will perform the largest planet census in history, expected to discover up to 40 times more exoplanets than we've found in the last 30 years. This isn't just an upgrade, it's a total revolution in how we study the universe. Meet the Nancy Grace Roman Space Telescope. Built on 35 years of technological leaps, it's not just replacing the past, it's going to answer the two biggest mysteries in physics. Why? Because 95% of our universe is made of stuff we can't even see. Dark matter and dark energy. Roman was built to hunt both, while catching rogue planets along the way. Believe it or not, Roman's primary 2.4-meter mirror actually started as spare hardware from a scrapped US spy satellite, given to NASA for free. While the mirror is Hubble-sized, the camera is a game changer. A 300-megapixel monster powered by 18 individual detectors. To show just one image at full resolution, you'd need 500,000 4K TVs. Weighing 8,000 kilograms, roughly the size of a semi-truck trailer, Roman won't orbit Earth. It's riding a SpaceX Falcon Heavy out to Lagrange Point 2, 1.5 million kilometers away. Why L2? Lagrange Point 2 is a gravitational sweet spot located 1.5 million kilometers behind Earth relative to the Sun. Here, the gravitational forces of the Earth and Sun balance out, allowing spacecraft to hover in a stable orbit with minimal fuel. More importantly, it keeps the telescope cold and blocked from the blinding heat and light of both the Sun and Earth, providing a pristine, uninterrupted dark window into the cosmos. Think of dark matter like footprints in the snow. You can't see the person, but you see their weight. Dark matter's footprint is extra gravity keeping fast-spinning galaxies from flying apart. Dark energy is the opposite, a force blowing up space like a baking loaf of raisin bread. Galaxies are the raisins, staying the same size while the space between them expands faster and faster. So, how do scientists actually measure these invisible forces? Dark matter and dark energy are both large presences in the universe that are only detectable through their effects on normal matter. The brightnesses of faraway supernovae work to measure the distances of galaxies and how dark energy is pushing them apart. The precise shapes of galaxies serve as a way to study the dark matter around them, but these features must be measured very accurately to be usable. Roman's hardware is particularly precise and well understood, so the data it collects is especially good for the statistical analysis required, giving scientists a holistic view of how dark matter and dark energy exist and affect the visible universe. To solve this, Roman has three main missions. First, mapping 600 million galaxies across 12% of the sky using gravitational lensing, where gravity bends light like a cosmic magnifying glass. Second, staring at the crowded center of our galaxy every 12 minutes to hunt thousands of exoplanets and rogue worlds drifting alone in space. How does Roman spot hidden planets thousands of light years away? Through gravitational microlensing. Einstein predicted that heavy objects warp the fabric of space. When a star with a planet passes directly in front of a background star, the foreground system acts like a gravitational lens, magnifying the background star's light. If a planet is orbiting that star, it creates a secondary spike in brightness. It's an insane cosmic alignment trick that lets Roman find worlds that are completely invisible to standard telescopes. Think of JWST as a hyper-powerful zoom lens, and Roman as a massive wide-angle lens. Roman scans the sky for clues, and JWST zooms in for the close-up. This mission honors Dr. Nancy Grace Roman, NASA's first chief of astronomy in 1959. She fought tirelessly to create Hubble and envisioned planet-finding tech decades before it was possible. Unusually for a flagship space project, Roman is ahead of schedule and under budget. Beaming down 1.4 terabytes of free, public data every single day, the next big cosmic discovery might not come from NASA. It might come from you. Ultimately, answering humanity's deepest questions like, where do we come from? And are we alone? Is too massive a task for any single telescope. That's why NASA is creating the ultimate cosmic team. Operating simultaneously at L2, the James Webb Space Telescope and Roman will work in perfect harmony. When Roman's wide-angle eye flags a mysterious exoplanet or a sudden supernova, James Webb can immediately zoom in to take a deeper look. Unlike Hubble, which orbits close to Earth and often has its view blocked, both Roman and Webb sit clear of Earth's interference at L2, giving them an unobstructed view of the deep cosmos. And when Webb spots a strange anomaly in a single galaxy, Roman provides the massive context of thousands of galaxies surrounding it. Working together, using each other's unique strengths, these two megatelescopes will push human knowledge further than ever before, bringing us one step closer to decoding the mysteries of our universe.